So conceptually, with Graham's law of effusion, it's basically the ability for gases to move through a small opening. So I always tell students, you can think of it as the helium balloons you get as a kid. So when you're a kid, you go, to a store or somewhere like a circus, they fill up the balloon with helium, and over time, the helium, right? The, the balloon expands based on the number of particles, and helium is less dense than air, so it actually rises. But the next day, what you notice is the balloon shrinks and it's a sad little ball on the floor. So what happened? Effusion. Over time, the plastic in the balloon has small pores and openings, and the helium escaped out of those holes. Now, why is there still some volume in that balloon? Well, you have to realize that some of the particles in the balloon are still in there. They're just traveling at a slower speed and some are moving in. And helium is smaller than oxygen and nitrogen and the other components of air. So it moves out first. And that's why it kind of shrinks, because it had a larger volume of helium. So effusion, you can think of it as diffusion or movement of gas particles through a small opening. Now we apply that to kinetic molecular theory, that gases are moving in straight lines, okay, at high speeds. Now, if we look at all gases, at a temperature, there's an average kinetic energy. And the average kinetic energy, it would be the same for all the gases, whether it be helium or oxygen or nitrogen, if they're at the same temperature. Now, in the videos this week, I actually talk about kinetic energy and I show that formula. They also talk about it in the gas laws, but it's also in thermodynamics. That kinetic energy, you can say, is 1/2 mv squared. So we can say helium has a certain kinetic energy and a certain mass. So helium has a certain mass and it has a certain velocity that it's traveling that we can square. So there's helium's velocity. And that represents the average kinetic energy of helium at a given temperature. Now that kinetic energy would be equal to the kinetic energy of, let's say, oxygen. So we would say 1/2 mv squared equals 1/2 mv squared. The kinetic energy is the same, but now we have to take into account, instead of helium, we have oxygen for its molar mass and its velocity. So when we look at these, the halves can cancel. We don't worry about the halves. So now what we're looking at, which affects, okay, the kinetic energy, there's two things, right? Well, temperature as well. So temperature is going to affect kinetic energy. If you increase temperature, things are going to move faster, you're going to have more kinetic energy. But let's just say we're at a constant temperature. The two things that are going to affect kinetic energy are the mass of the particle and the speed. Okay? So
Right.
so let's look at helium. Let's look at the molar mass of helium. Molar mass of helium is 4 grams per mole. And I just look at the periodic table for that, right? And that's because helium is a monoatomic element, and we would have helium's velocity squared. And then over here, what about the molar mass for oxygen, which is a diatomic molecular element? That would be
It would
30,
be 32.
exactly, moles velocity squared. So when I look at this, we see that they have the same kinetic energy, but it is obvious that helium has a much smaller molar mass. For helium to have the same kinetic energy, but a smaller molar mass than oxygen, what does it mean its rate has to be?
It would travel, wouldn't it travel faster?
Exactly. So that is the key that you need to understand, is that smaller particles are moving faster at the same kinetic energy. So even though they have the same kinetic energy, because they're smaller, they have to move faster. And because they're moving faster and they're smaller, they typically effuse quicker. They escape the small openings faster. And that's why the
Right.
helium balloon is a sad little balloon that my kids would kick the next day because they were all angry, right? Because it doesn't, okay, that's just a joke and it's a bad joke. But going back, how do I apply this to Graham's law of effusion? So you understand that conceptually though, right?
Yes, I do.
Okay, so now what we're gonna do is we're gonna say mass of helium, we're gonna go back, velocity of helium equals the mass of oxygen, velocity of oxygen. And we want to look at this in terms of rate. So we know helium's going to be traveling faster, right? So what we can do is we can manipulate this equation right here to solve for a proportion, the rate of helium over the rate of oxygen. Does that make sense? Because we know we want the bigger number, the speed of the helium, in the numerator so
Yeah.
that the denominator is 1. So whatever the rate of the denominator is, we can divide it into the bigger number and have 1 in the denominator and just have a proportion be bigger than 1. Does that
Okay.
make sense? So
Yeah.
I'm going to solve for velocity, which is a rate, right? Distance over time, like miles per hour, a rate. And I'm going to
Right.
solve in terms of velocity of helium over velocity. So I would divide both sides by the velocity of oxygen. So I get the velocity squared of helium over the velocity squared of oxygen equals. Now I still have the mass of oxygen over here, and I'm going to divide both sides by the mass of the helium. Does that make sense?
Yes.
But now I want to get rid of that squared. So what do I do to both sides?
That's what I don't know.
You take the square root,
Okay.
right? So if I had x squared equals 9, how would I solve for x? I take the square root of both sides and I get x equals plus or minus 3, right?
Mm-hmm.
So I got to do the same thing on this side or with this equation. I got to get rid of that square, so I have to take square root. So I square root this, I square root this. And what the Graham's law of fusion shows it at is they'll say rate of helium over rate of oxygen. Really, the rate is the velocity.
Okay.
Right? Equals the square root of the molar mass of oxygen over the molar mass of helium. And it makes sense that the lighter one, the molar mass, is on the denominator of the opposite side, right? Because the molar mass of oxygen is bigger, but the rate of the lighter one's on top because it's traveling faster. Now, the way they write it for the Graham's law of infusion, they don't actually put the gases in there. They'll just say rate like 1 or A, gas A, over rate gas B.
Right.
So the rate of gas A is usually the one traveling faster because you want the number bigger than 1. So who's going to be traveling faster? You said it earlier, helium or oxygen.
Helium. The
So,
helium.
so that when we go to molar mass, and the way they do the molar mass, I'm not very, they do like a cute little M. I just do M and M, molar mass.
Right.
You know what I mean? It's just easier. But the molar mass of A is going to be on the bottom over here, and the molar mass of B is going to be on the denominator there. So that's how you plug it in. So we can change the gases, but the
Right.
rate, the comparison of the rate is you're using the molar masses, you put it in a ratio, and you take the square root. Does that make sense?
It does. I just need to make sure I'm doing it in the calculator correctly.
Okay, so let me let me stop the conceptual aspect of Graham's law of effusion. So if people get that and they don't want to watch the rest, they don't have to watch it. But I'll start it up again and we'll do the actual calculation for you.
Okay.
Okay, so let me stop this.